the video about fundamental theorem of calculus, but second part, where we're going to be practicing some examples. And this actually might be the last topic in your Calculus 1 class. In many schools, we finish on this at this topic, fundamental theorem of calculus, where we try to differentiate the integral, basically reversing the process. If this is the last topic in your class, congratulations, that means you are almost there. So, long story short, we're going to teach you how to differentiate the integral d with respect to dx, that's the notation for the taking a derivative, and that's a differentiation process, of the integral from a, which is fixed left endpoint of the interval a, but up to x, that means the right endpoint is not fixed, it's a variable. And then inside we have a function f of t dt. What happens when you differentiate the integral? Then you basically get the function inside, but instead of f of t, where t is basically a dummy variable, you will get f of whatever is here at the upper limit of integration. Since it's x, you get f of x. That's what's happening. And just to remind you, the idea is pretty genius. We used to integrate only from a to b, but now we want to have this b, the right endpoint, to move left and right. So it means the area will not be a fixed number anymore, like pi over 2 or 7 or 35. Now I can move it. In the moving to the right, I'm adding more area. Moving to the left, less area, and so on. And that's why the area became a function, and we literally call it the area function. It's always also called a cumulative function because it accumulates the area. It's a pretty cool idea, and in the future you even learn what's gonna happen if x goes to infinity. Now, let's practice some examples. Find a derivative of the integral. That's one of the ways you might see the notation in your homework. Or you might see this notation, find d over dx of the integral. I like this notation more, so don't be afraid if you see both. Derivative versus derivative notation shows up. I build cases for you. I always teach using cases, and then you know that it's not that straightforward all the time, and you need to take into account those cases. So, case 1 will be called just plug in. Sounds pretty simple, and it is actually simple. Just plug in. So the idea is when doing integration by differentiating the integral, I will ask you to find d over dx integral from any kind of number, so that's my notation for any number, 5, 10, 13, minus pi, doesn't matter, to x, x is my upper limit of integration, a variable, of t squared plus 5t dt. So, in this case, since we're integrating the function and then we're differentiating the result, we're undoing the integration, and since we actually differentiating not a number, because definite integral actually gives you a finite number like 17, right? It's the area. But since we're working with net area or changing area or area function, right? Remember? Area function. That's why when we're differentiating that area function or accumulative function, the derivative is not 0. It's actually some kind of function. What kind of function is that? Just take this upper limit and plug it everywhere you see your variable. So in this case, t is the variable. Then the answer will be x squared plus 5x. Kinda that's all. That's the whole magic over here. So the point is just plug in. That's good. Seems like there's nothing happening right now. But guess what? What if I'm gonna, case 2. What if I'm gonna be a left-hander right now? If there are left-handers watching this video, maybe they will understand what I mean. When I was listening to this topic, I asked myself, why are we fixing the left endpoint and the right one is being so fancy and moving left and right? And then the areas keep accumulating on the right, right? What if I want to reverse it? What if I want to fix this right endpoint and move the left one? Yeah, you can do that. And that's what we're going to do right now. And as always mathematicians do, we're going to create a new case, but we will solve it using the previous case, case 1. And I call it flip. Flip in this case. I'm talking about find derivative d over dx of the integral where x, left endpoint, is the variable and the right endpoint is the number, say some kind of 0 or pi or whatever, b. Yeah, I actually can even call it a, some kind of any number, and in this case it's b, to have more beautiful annotation. And the same function, t squared plus 5t dt. That's pretty cool because basically it gives me a chance to be more creative. In this case, I'm fixing b, the function even stays the same, but x is keep running left and right, and now I'm accumulating to the left. The more I add, the more you add, the less you add, the less you add. So it depends how x is going, to the left or to the right. Well, how to go from this case to this case? Because that's what usually we do in mathematics. We use, when we create product, we use addition to figure out product. And when we use division, we use product. So we like accumulating knowledge and use previous knowledge for the new knowledge. In this case, there is a property of the integrals that tells us that I can differentiate instead, who said something? Minus integral from b to x, right? That's the properties of the definite integrals. You can switch limits of integration by putting a negative sign in front of it. Then it will be case 1. Also, properties of derivatives tells me that I can kick this constant outside of the differentiation, because the derivative of minus 5x is the same as derivative of minus 5x, right? So that's the same thing. Then the rule still be the same. Minus will be outside. And then case 1, just plug in. I'm taking this x at the top and plugging it everywhere I see t. It's going to be x squared plus 5x. Which means now it's negative x squared and negative 5x. That's all. Nothing super crazy over here. Compare the positive answer and the negative answer. Not too bad. Case 2 was not too bad. And it was all very nice and fun until, guess what happened? Chain rule happened. So chain rule kind of messes everything up. It's not messing it up, but it's making it more complicated, of course. It's always been like this. Learning chain rule was a pain. And then it became pretty interesting. And if you watch my video about chain rule, you will find out how chain rule is used in AI, and teaching computers how to learn and how to work for human beings. Chain rule is actually used there. So, just to keep going, the chain rule case will look like this. If I have the same derivative of the same integral from a to, and the same function, t squared plus 5t dt, but at the top I will have, instead of x, I will have x cubed. That's chain rule. Because basically now we're differentiating not from a to x, but from a to x cubed. So this is what we're going to do. We're going to plug, just like we plugged before. So I will even write it down for you in orange. You still plug in, like in case 1, and multiply by, guess. So if it's chain rule, what do we always multiply at the end? By the, yes, derivative, right, of this troublemaker. In this case, it's x cubed. So let's do it. The first step says just plug in. You see the red color x cubed? Here it is. I'm gonna plug in x cubed everywhere I see t, just like it says plug in. Plug in. Because chain rule is basically function inside of the function. And before, in this case, x was inside of the function, t squared plus 5t. Now, x cubed will be nested inside of the function t squared plus 5t. So, I will have x cubed and then squared, because it's t squared, plus 5 times x cubed. And that's almost the answer. You're almost done. But then don't forget the last step. And multiply by the derivative. Times derivative of x cubed is 3x squared. And this is the answer. Kinda that's all. We don't really want you to be fancy here. Don't even need to distribute if you don't want to. But at least I will write down x cubed and then squared gives me x to the 6. X to the 6 plus 5x cubed, everything times 3x squared. Or you can distribute everything. 3x, 6 plus 2 in this case, gives you 8 plus 15x, 3 plus 2, that's 5. Both of these are good answers. So case 3, chain rule. And it's basically the most complicated case we're going to show you all the time on exam problems and homework problems. Just to make sure you don't forget what chain rule is. But there is one more case, which is basically a combo of all the cases I just mentioned. Case 4. And combos are always fun. And I'll call it a break. So, it will be example like this. A function, I will even put it in the green because it will be just a notation. D over dx, so I'm differentiating the integral. And at the bottom, I will have a function. And function number 1, I will even call it function 1. And at the top, I will have function 2. So, like here, the case before, I had from a to x cubed. So at the top, I had a function called x cubed. What if I have functions at the both sides? What is your idea how to actually figure that out? And here is my notation to help you out with this. You can take integral, you can first, like this. You can differentiate instead integral from a function 1 to any kind of number. First, any number. I will call b, why not? B can be anything, and actually you are not anything, you will see some exceptions at some point, but b, you choosing the b. Plus, then what's gonna happen if I'm making a break? That's why I call it a break. Yes, exactly, plus integral from b to function 2. And that's a property of the definite integrals that you can break at points. If you're working from a to, in this case it's not a to b, if you're working from, I don't know, c1 to c2, and it's not convenient for you at any point, I can choose some kind of b and then integrate from c1 to b and then from b to c2. Then the second integral will be case 1. Actually, it's going to be still chain rule. So it's going to be case 2, right? And the first integral will be case 2, but you have to flip it. So I will do minus case 2, because you want to have from b to a function. Make sense? Let me show you. Example will look like this. The same, I will do like this. I have a pretty cool example over here. D over dx from x to the 4 to x to the 5 to t minus 1 cubed dt. Okay, I know it looks crazy, but let's do it carefully step by step. And basically this example accumulates everything we just learned. So I don't like it. It is from function to a function. I know how to handle the integrals where one of the sides is the function. You will just plug it in and then times the derivative of that function. But both sides is not very good. So I'm gonna break it like this, like I mentioned to you. And I will just make a notation like in different color because it's not very legal notation. So I will just do like this. It will be integral, a derivative of this integral from x to the 4, and I will choose 0 to break it. plus a derivative of the integral from 0 to x to the 5. And this 0 or 5 or any kind of numbers, if you notice, they never actually mattered. Every time I was working with derivative of the integral, this a or whatever it is never mattered at all. That's a pretty cool part of it. That because we're talking about the function regardless of the interval before we started integrating or differentiating it. It's just a free floating function in the air looking like this or somehow. And then the interval is created when we start integrating it and then differentiating it. So if we are doing all those processes, the function is not supposed to depend on the limits of integration, which are constants, a, b, and so on. So going back to the example, I'm choosing 0 and it will not change the answer. So the first integral, I will flip it and I'll write down that I'm flipping the first one. Now it will be derivative of the integral from 0 to x to the 4. I flipped it, you see? I flipped these guys by putting a negative sign. The function stays the same inside 2t minus 1 cubed dt plus, and the second integral is still the same, so it's going to be d over dx from 0 to x to the 5 2t minus 1 cubed dt. And now I plug and then multiply by the derivative of these functions, x to the 4 and x to the 5, based on chain rule. So this step is chain rule. Chain rule. What is going to happen? I'm going to plug x to the 4 everywhere I see t, and x to the 5 everywhere I see t. And for each case, I will multiply by the derivative of the upper limit. The first integral derivative of the integral has negative sign in front of it because we flipped it, and it's going to be 2, and I'll put in a red color, x to the 4 minus 1 all cubed, not squared, cubed, times the new piece is gonna be in orange. Derivative of the function of upper limit, that's gonna be 4x cubed plus 2 in red color, plugging x to the 5 minus 1. Everything